I've followed this biofuel saga since 1980, the late 70s. And I have to say, over the years, my views, my assessment has gone through cycles. And I think this meeting has been very influential for me in thinking through how do we address biofuels. And when you think about it, the reason, at least on the liquid fuel side of it, liquid and gaseous fuel side of it, we're talking about transportation applications. It can be used also, obviously, for many other purposes. And when you do that, you say, okay, as I did in my presentation, I talked about, okay, there's about 20% of current transportation energy use that really that we don't have a solution for. And to ignore so just starting out at that level, if we ignore biofuels, we're really handicapping ourselves and looking toward the future. So it's almost like we need to look at it seriously, if only because it is at least a leading, if not the leading candidate. And if you look at, do a comparative now, just compare it to hydrogen, for instance. There's almost no scenario that I've seen going many decades into the future where that cost comes down much less than what, I don't know, Joan, $7 a gallon equivalent, right?
I think if you look several decades, you can get lower than that.
A little lower than that?
Maybe, yeah, 4 or 5.
Okay, so, using that as a benchmark, and that's not even clear, that's going to be available for some of these applications we're talking about. And you look at biofuels, and the problem with biofuels is, as Lee just said, it's always, we're aiming it for, next year or 2 years from now. And I know my university, UC Davis, has been one of the leading researchers in advanced, certainly in agriculture and biofuels over the years. And I've watched it. It's so cyclical. And the money just goes in, it goes out. There's not been a continuity in the R&D, and it's not been long-range focused at all. And we've seen the problems with that. So I'd say, okay, number one is we better really refocus on this because this is one of our best options, and we don't have any other really good option foreseeable. And all the cost estimate forecasts you look for, I mean, Lee didn't go into in great detail. He started getting at it, but there's lots of them where you end up at $4 or $5 a gallon equivalent easily for the advanced biofuels, and even without some of the more aggressive R&D kinds of ideas that Lee was talking about. So that's number one. Number two is that there is a lot of land out there, and it's gotten politicized, this food versus fuel issue, but there's a tremendous amount of land there first of all, there's all the waste from forests, ag residues, municipal solid waste, as we talked about, and okay, that's not going to give vast amounts of energy, but we could probably get even 10% of, maybe 5 or 10% of today's energy from residues and waste without too much trouble, maybe more. And okay, that'll be a good one for Chris to respond to. But there's some number there, and we're not talking about massive, as we go in the future, we don't need to replace all of it. And the number three is what Chris said about beef. So I've got a beef with beef. Put a tax on beef. Beef is by far, all the numbers I've seen, and Chris can hopefully confirm it, is a vast amount of land, a vast amount of the greenhouse gases are associated with beef consumption. Put a tax, okay, all the economists in the crowd, here's something for you to focus on. Put a tax on beef, and let's see how elastic the behavior is on that. And the last part is just just summarize, R&D, I think, and the theme of this event is we need sustained R&D that, will really address it. And we've not, and I would argue, we've done a poor job of that. BP put money into Berkeley in Illinois for a little while, and came and went, and there's a lot of stories like that. So there's a lot of opportunity, I think, that, and Lee has one good idea, and as he suggested, there's probably others. So I think we need to be much more upbeat about it, even taking into account all the other social, ecological impacts. I think this is an important thing that we really need to put a lot more focus on.
That's a lot, so I'm not going to comment on all of it. I'll just sort of comment on your final point, which is tax beef, and in fact that would actually have the effect that you're proposing. And I will point out that when we were discussing where's the land come from in these models, there's no new land created in these models. You actually have to deal with what you have. And again, it depends on the policy frame, but when you value the carbon in the terrestrial system, just at exactly the same value as you value it in the remainder of the economy, that price of carbon gets propagated through the entire system, and what happens is that you eat less beef, and the diet shifts to other forms of protein. And in general, that's where the land comes from. And the model is, in fact, is executing your proposal. Chris, you want to comment?
Go ahead, Chris.
So, one of the things that is interesting when we talk about multiple uses for the biomass energy that we do put into the energy system is that the two talks that Jay and Lee gave actually provide alternatives. They both can get you to the transportation problem. It could be that the way you solve your 20% of transportation is to continue to use fossil and offset it with BECCS. Or it could be that the way you do it is with advanced biomass-based fuels, and you get the same thing, zero net for transportation. And at this point, it's not obvious which way we should go. I did want to speak to this question of is there a tremendous amount of the resource out there? And the answer is there is a tremendous amount of the resource out there at the scale of energy equivalent of tens of exajoules. A lot of energy, very, very small relative to the global energy system, which is like around 600 exajoules per year. Is that the current number? And so we might be looking at order, easy to see where you fit in 5% of the global energy system. Once you go above 5% of the global energy system, you're running up against the other competing land uses, and grazing certainly one, protection of natural ecosystems is another. And one thing we didn't really talk about is a real challenge with producing biomass for energy in low productivity areas is it takes a lot of energy to harvest it. And a typical way to think about energy that you might harvest from food-producing land is that half of the biomass stays below the ground. Of the half you harvest, half goes into the part we eat, which is a really consistent target in what's called the harvest indices. And maybe you could get half of the energy in the part that you shift to the energy system as primary energy. That means you're to the 1/8 of the primary production. And once you're to 1/8 of the primary production across vast areas of land, you're still only at the less than 10% of the global primary energy system.
Yeah, keep in mind that transportation is what, maybe a quarter of the total energy.
Yeah.
So we're talking about 10% of a quarter, so we're really talking about 2%.
Right, I think we're saying the same thing, but it's important to put it in the context of the total amount that's available. And if you're going to get your 10%, then I'm not going to have the 100 exajoules to put into BECCS in addition to that.
Although as I pass this down, I will say that when you go to the transportation, what you would want to do to minimize the footprint is actually put a CO2 scrubber on the refinery, because you want to pull that carbon off so you don't actually have to displace it. And so you actually would, in some ways, you would go after both of those simultaneously.
There's a tremendous gap between what I think I understand about this field and what most people think they understand about this field, just right or wrong. And so I have to be careful about not taking too much time to look at those gaps. But let me comment on some of the ones I see. So With respect to whether biomass is or could be a carbon neutral technology, I could tell you the long version of the story, but I'll tell you the short version, and that's this. If you start off with an ecosystem that has a lot of stored carbon, and even if you convert as much of that as you can to any form of bioenergy, electricity or liquid fuels, you would very often do better to leave that ecosystem there. In other words, you're worse in the year you harvest the ecosystem than you would be if you left it alone. However, if you grow grasses, which don't accumulate above ground carbon, you do not have that problem. So once again, like everything else in bioenergy, if we do it wrong or heedlessly, can we screw it up? Absolutely. But is there a way to completely avoid that? Yes. Indirect land use change was originally projected as being 150% of the emissions of the gasoline base case. In other words, it was a sign changer. Today, the estimates cluster for both corn and cellulosic ethanol at about 10%. It's no longer a sign changer. It's still something people talk about. How to incentivize this is a big issue, but it's sometimes understanding lags, perception lags current understanding. So I think Chris gave a very fair view. I know people that are much more critical of the potential of bioenergy supply, Chris, and I suspect you do too. I also know people that are much more favorable about it. I mentioned previously, without any pre-selection, I recently tabulated 5 low-carbon energy scenarios: Global Energy Assessment, IEA, Greenpeace, World Wildlife Fund, which actually had the highest amount of bioenergy. They averaged 25% of primary energy supply. The lowest was 15%. So what that tells me, with the exception, I mean, you know, Jacobson and DeLucci are an exception, but most people who look at how they're going to make this whole system work, they find a place for it. So there are strategies to make a larger contribution than the things that Chris described, I believe. I'll just briefly allude to a few of those. Certainly at some point, other things we care about push back. There's no doubt about it. I think it's extremely hard to tell what that point is in advance. I think it's really clear we need some of this. So I think we need to sort of safeguard that we don't overshoot, if you know what I mean. But I mean, for example, you can greatly exceed, as you acknowledged, Chris, the productivity of natural systems if you put inputs into them. And it's true that if you use Haber-Bosch to fix nitrogen, it's got a big energy price. However, if you look at a biomass refinery from which electricity and fuels would leave, there's no nitrogen, there's no phosphorus, there's no potassium. It's vastly cheaper to recover those nutrients in the biorefinery and put them back in the field. You've already got trains and trucks coming in, bringing in your feedstock. You put a few sacks of stuff on the back. I'm not saying it's free, but it's possible to be much higher than the natural carrying capacity without once-through nutrients. That's just one example. And again, I have to be careful to not say too much. I think there's a whole lot of, oh my goodness, there's a whole lot about, I gotta say this. Does anybody know, so as you indicated, the amounts of pasture land in the world that people estimate are between 3 and 3.5 billion hectares, depending on who you look at and how you define pasture. It's one of the most ill-defined land masses in the world. The data's terrible. Does anybody have a guess what fraction of global dietary calories come from that land? According to the leading expert on this, Mario Herrero, it's less than 1%. So of the land we use to feed people, we actually feed the world in about 1 billion hectares. As far as global food supply, now food security is a local issue, not a global issue. There's a tremendous amount of land that we're getting very, very little food from. In Brazil, they tripled beef, the biggest pastured beef producer in the world. They tripled beef production in 20 years. Did they add more inputs? No. What actually happened was, according to Geraldo Marta, who's at Embrapa, one of the experts, what actually happened was he said, you know, at the beginning of that period, our economy was, we were in a dictatorship. Everybody knew it was on the way out. We had tremendous inflation. So land and cattle were both hedges against inflation. And it was only once that settled down we started to worry about actually getting a lot of output out of this land. And they tripled productivity in 20 years. I'll talk about diet later. But the last point on...
Take some other questions.
I understand, and I'm sorry, I apologize to begin with. In Africa, the primary land use, agricultural land use, is for cattle. They don't eat much cattle. It's a banking mechanism. Imagine the footprint of smartphone banking and how that would make land available. So there's a lot we could do.
Hi, I had a clarification question for Chris. You mentioned 80 to 250 exajoules a year. Could you, first of all, say what that, again, remind me what that figure refers to and explain a little bit about the range and what went into it?
Sure. Well, it's actually, Jay can say more about that number. That's what I'm seeing is the range of BECS in end of century IAM runs, just in general. If you say what, Jay gave an eloquent explanation of why the models want to do it, and that's the levels that we're seeing.
Okay, great, thank you.
Also, just to help people on the units, 80 to 250 exajoules per year is something like 3 to 8 terawatts. Yes.
I think a little more of a technical question. Try to stay out of this debate, although I have my own opinion on it. But if you look at another very recalcitrant carbon form, it's coal. And people there managed to convert that to gasoline in the end, and I would argue that's around $75 a barrel equivalent. You can do that, and Sasol is doing this. So my first question then becomes, if I take that as a standard, because I would assume you can do this with biomass, how do the alternatives actually compare to that?
You want to talk to the chemistry though?
Yeah, and I will, just so I can give a brief answer. The Fischer-Tropsch process that Sasol uses, they used to produce anyway a third of their liquid fuel from coal. You can in principle do the same things with cellulosic biomass. They very much benefit from large economies of scale. There are experts who would tell you that that is probably going to be cheaper than biological processing. I believe biological processing will probably be cheaper, and there's a certain elegance as you're actually more embedded in nature's carbon cycles and mechanisms. You have a biological process, you're not likely to make something very biologically unfriendly, for example. But if your question is, could we use thermochemical methods and might they be competitive at a reasonably low price, as Dan mentioned, I think the prevailing evidence is yes. I'm not sure if there's more to the question than that.
Well, in part, I just wanted to compare where they are, right? And in the end, you're making liquid fuels, so they are not all that environmentally friendly, no matter which way you slice it. Whether I'm burning a biodiesel or a diesel comes down to be not all that.
I'm not sure they're so unfriendly. 15 years ago, Don German wrote that any reason to go to a different propulsion or fuel would have to be other than air quality. So I'm not sure what other thing you're going to be sacrificing with liquid fuels. I mean, we can make them as cheap to use, as clean to use as we want them, but...
Yeah, but therefore, that opens up the Fischer-Tropsch route. And I would argue if you're thinking 50 years, the scaling issue could be looked at.
It's a competitor. I think realistically, as far as where they are now, I think the bands of uncertainty, which all things considered have a lot of different contributing factors, would overlap. And so as far as where the technology is today, I think biological conversion and Fischer-Tropsch are in the same ballpark.
Okay, thanks.
I just have a quick clarifying question. Just to say, I think the overwhelming kind of cost of large-scale Fischer-Tropsch conversion is in capital costs as opposed to in inputs. You are dealing with higher costs of biomass inputs compared to coal, maybe $80 a metric ton as opposed to $10 a metric ton. But I think there actually are some R&D needs to do large-scale Fischer-Tropsch fuels from biomass, primarily related to biomass logistics and then large-scale gasification. We use large and shrink flow gasifiers for coal gasification, usually oxygen-fed if we want to do that. And we don't know how to do that for biomass yet. So there is an R&D need around large-scale gasification that we haven't figured out.
Okay. So my question is really for all of you. I'd love to hear your thoughts on how and whether we might program into the development of new technologies, fuels and technologies, kind of program into them program into them risk mitigation, right? So Chris, you talked about why this technology has some inherent risks associated with it. And we've seen, based on many historical examples, that regulating a technology or an industry is quite difficult. So sort of providing the technology and then coming in at the end and regulating it is tricky, right? It's a coordination problem, very difficult to solve. And, you know, a carbon tax could help, but then as both Jay and Chris mentioned, there are some complications there and sort of understanding ex ante what the results would be. And then Dan mentioned the need for R&D, and and sustained R&D. Absolutely agree with that. But I think it needs to be informed or directed R&D. In this case, I think this is a prime example where, you know, we want to understand the risks in advance. And so the question is, can we program into our R&D efforts risk mitigation? And this question is also directed toward Lee. You know, can we think about what technologies, what fuels we're developing, and really inform that in a way that we haven't done before? I sort of see the conversation happening at two different levels, and I want to bring those levels together ex ante in, you know, the development of technologies.
I might start with, you know, your question is an excellent one. I'm not sure we can give a systematic answer here today, but one of the things that's most challenging ethically, technologically, and economically about the whole BECS paradigm is that essentially we're saying that what BECS does is it allows us to ease off the accelerator on decarbonization in the near term with the idea that we can augment near-term emissions reductions with long-term negative emissions. And so in some ways it's not only saying that there's a financial transfer across generations, but there's kind of a responsibility transfer across generations. That's something that we're not generally looking at with the other technologies. And I would say that it's not something that we've grappled with in a responsible way. I think the risks from mitigation technologies, writ broadly, is going to be an increasingly important part of the societal discussion, and finding ways to provide management of that risk certainly has to be a part of the way we think about the future. And I think the more quickly we embrace that idea, not only looking at downside risk, but also opportunities for co-benefits from various technologies, is going to make the dialogue a lot more constructive and a lot more efficient.
Yeah, I also want to say that you're absolutely correct as far as I'm concerned, that particularly in the area of bio, where you have so much interconnectivity and there are so many things that are affected by the way it's deployed, by the scale at which it's deployed, where it's deployed, how it's actually being used. And you know, I think your point is very well taken, that what you want to do is, rather than just choose some way and, you know, sort of work it out, let the world sort of experience it, and it, you know, see if you like that, and then, you know, then start over if you don't like it. Rather, it's I think one of the major elements of a research agenda is to start thinking through systematically what are the different ways that this can be deployed. Because if you do want to go to zero, even if you don't want to, you know, and I think Chris makes a good point, that there is this moral hazard that you have. Oh, I've got a potentially powerful engine that, you know, if I mess this up, I can get back. You know, but in fact, we know because of the system lags and all, you're probably not going to really get back. That you don't want to fall into that trap, and you do want to think through these implications before you actually get this out, and before actually you get a carbon price that is high enough that this thing could actually take off and move to scales and deploy in ways that we wish we had thought it through before.
All right, we have about 20 minutes left and quite a few signs, so we can speed up the Q&A. Quick two-finger thing,
I need to say something about that. I'll try to be brief. Let's be clear. The risks that I think most people are concerned about are not associated with the technology. They're associated with the deployment of the technology.
My point is that
Hold on. You could take the same technologies and deploy them differently, and you'll have them. And in my opinion, the main thing we need to do is to start actually doing projects where we're targeting in sustainability benefits, including to humanity, to humans, people. I don't think it's that amenable to an analysis. In theory, we already know the right things to do. We need to come up with the business models and the regulatory frameworks that make them happen. And the way you do that is to do them, realizing that these are small and the mistakes aren't that big.
Can I just add something to that? I mean, I think we can do those kinds of analyses, and your comment on grasses is a step in that direction. Right, so, and I'm not just talking about BECCS, but generally the use of land and biomass as an energy source. And so, anyway, I just think we have this. I'm just so happy to see this range of experts here, and it's so rare that you have. So this is, I think, a prime example that we can
Trust me.
Okay, let me briefly come back to this moral hazard, and we are shifting responsibility to later. I think it's a great argument you could have made in 1980. We are already in the middle of it. If you really, and I heard you say this sort of maybe 1.5 degrees is not such a good idea, or 2 degrees is not such a good idea. Maybe we find another place, right? That's basically saying, if it's really 1.5 degrees, we need those negative emissions now. This is not a question about, oh, we can push this back into the future. This is about right now, right? We need to start balancing the books and come out on the other side. We may already have to come down. If 350p.org is right, I don't see how we can get there without negative emissions right now. If 400 is the right number, it's too late. And I would argue 450 is already too late. We need to start pulling back, and we need to be fully aware that we will have an overshoot which will hurt and will cause irreparable damage which we cannot change anymore. So in many ways, we should view this as a waste disposal issue, and we are leaving waste on the table every day, and we need to get rid of it.
So this may just be a more granular version of the question, but my question is, what would you say is the state of health of the emerging biofuels industry today? And the reason I put the question that way, across my email yesterday, it turns out that MIT Engine Initiative 2 days ago published a study describing and analyzing all the failures of venture investment in clean tech over the last decade. And what they had to say about biofuels, was that although there were a couple of notable examples that at least got to the point of maybe paying back investors, and so the specific examples were Amiris and Kior, which reached the IPO stage. At this point, Kior's gone bankrupt, and Amiris is at 1/10 of its IPO value. Right? And so my question is, are there other bright spots? I mean, or is it a complete retread of the technology of the kind that Lynd described that's necessary at this point? I assume that those two failed because of they got crushed by falling oil prices and natural gas. Right?
They actually they crashed before the oil prices, so that was not the reason. They crashed because of overhype primarily and under delivery. The field is the cellulosic biofuel field is close to dead. The 4 IPOs that were offered in 2000, that came out in 2011, are all way below their initial offering price. People got fired who recommended those investments. So that doesn't necessarily mean that that the only opportunities are as radical revisions as the one I suggested. There are ways forward, but it's hard to exaggerate how down the field is.
So we have to wait for institutional memory to fade.
It drives me a little bit crazy to hear people say sometimes about that, and I haven't heard it about bioenergy here, but the technology is not the problem. Well, the last time we got people excited, the technology was the problem. And meanwhile, we're not working on the technology now, and someday institutional memory is going to go away, people are going to get excited again, and then technology will be the problem again unless we actually do something. So,
Let's go, Dan.
Great. I had a quick question, primarily for Jay, and this is about how we think about biomass allocation in integrated assessment models. So, as we've mentioned, there are lots of different things that we can use biomass for. You can make gas, you can make fuels, you can make electricity, and I'm wondering if the results of IAMs match our expectations that we need liquid fuels to come from biomass, or if we're seeing integrated assessment models drive towards other end uses. I would just add, specifically with BECCS, the different end use you're getting has a different amount of biogenic carbon capture. You know, you're only getting 40% of the carbon if you're making fuel. You can get 100 or 85 to 100% of the carbon if you're making electricity or making hydrogen. And I'm wondering if that impacts these outcomes.
Yeah, just to quickly answer that, the models don't do winner take all. They actually will distribute the bioenergy across a variety of different uses. Probably the largest, given what is in our model, and I can't speak to all of the models, but what's in our model, and the cost, and it all depends on cost and performance, the largest single user of bioenergy is the refining sector. It's with a CO2 scrubber on the back end, so that you actually do meet the transportation needs, because that's where the highest value application is. It's the most difficult for the models to get the carbon out in some other way, and so that's where it goes. I'll make one other quick point, which is obvious, but I'll say it anyway, that when you have the CO2 option available in conjunction with bio, the footprint from bio is smaller. I mean, it's obvious, but I'll just say it anyway, that you actually have a smaller footprint, because you can actually meet your carbon goal with less bioenergy, because you meet your transportation needs and have stripped off all that carbon that would have otherwise have gone back in the atmosphere.
Stephen, and we'll go to this one.
Just to maybe return to a point I started to make yesterday, and to ask this as a question, I'm interested in understanding how the models that you guys are talking about can take into account potentially the fact that the discussion this week has been very human-centric and presupposes, I think it's at least implicit in the discussion, that if we could just crack the code on climate change, everything would be okay. And I think if we had some forest ecologists in this room, they would tell you that nothing that's in that forest can actually leave if you want a sustainable forest ecosystem. That if you were with a prairie ecologist, and they understand our prairies, they would tell you that you can't continuously harvest it. And if you were to go hiking, as you can around here, into some of our national forest land, and you see where it's pastured, and 90% of our national forest land is pastured, it only produces 8% of the beef, the land is wrecked. And so how do we take into account that perhaps the ecosystem was in great trouble before we started focusing on climate change, and that we can build that into the models to say, well, if we had those voices in the room, they might start to be arguing for facts that we'd be much better reforesting our lands, repasturing our lands with sustainable and not untouched prairies, so that we are actually dumping carbon into them and avoiding the problem that we make, the unintended consequences. So I buy the idea of Jessica and others that we need to understand now what those unintended consequences are, but it feels like, is there a way that the model could take into account that others may have a different starting baseline on where we need to be with our ecosystems?
I'm a grassland ecologist. So it's not that the voices aren't in the room. And, I think that we haven't decided how much we're going to value ecosystem resources. I think that the paradigm that I heard coming from all of us was that when we look to expanding the biomass energy opportunities, we're looking within the 4.5 billion hectares that we're already using intensively, and many ways have already wrecked. The specific number I gave you, that 500,000 hectares, that's the land that has been used for agriculture sometime in the last 300 years and has been abandoned. Land that, from a kind of a ethical stewardship type of a perspective, we have both a responsibility but also an opportunity to improve.
Very quickly, if I may. The
I don't think it's a modeling issue. I think it's a policy issue primarily. But I would be very specific, and I think it's worth keeping in mind. The magnitude of the carbon mistakes, even carbon, let alone habitat mistakes, the magnitude of the carbon mistakes we can make by lousy land use without biofuels is comparable to the magnitude of the carbon mistakes we can make by lousy decisions in the energy sector. And there's a lot of evidence for that. What that means in a policy context, and I know Nathaniel Green is very worried about this, if we, and it's again independent of biofuels, if we regulate carbon and energy, but we don't regulate it in agriculture and land use, we will make a lot of perverse incentives. And so we can simulate it and model it, but we also have to realize that here again, the world's not going to do the right thing without valuing stuff, without valuing the right things.
I have two questions. One's a follow-up on this issue, and the other one's just a clarification. The clarification one would be for Chris, in that I would just want to understand whether or not the available land also included an implicit projection of agricultural efficiency improvement to feed twice as many people, or this was a static picture of the way it was now. So how would that affect things? The other question is for Jay, because I believe that the harmonization between what Chris is trying to bring up and what Steve brought up and what's in the IAM that leads to such large opportunities for BECCS is an unpriced externality that is not included in that all biomass feedstocks are treated as the same cost, and you don't include, as an economist, the externalities of deforestation, removing ecosystems. And so if you actually don't include those costs, then the model spits out this enormous opportunity economically for BECCS. But if you included the cost penalty as an economist of getting into land that otherwise has lots of other costs associated with it, it wouldn't do that. So I think that you need to clarify whether or not, in fact, it's a flat cost no matter where it comes from, and that could be rectified, or it actually has that in there. Those are two questions.
So in response to this issue of whether I explicitly included increases in ag yields, it's a great topic. I didn't specifically say anything about it because at the same time we're talking about a tremendous need for increase in ag yield and at least some opportunity. We also are looking at a tremendous increase in demand for the products of agriculture, including what history tells us is an increasing demand for the less efficient end of our ag system, which is meat. At the same time, there are also opportunities for harvesting additional residue from increased ag yields. And at the same time, we are looking at climate change projections that make it more and more difficult to increase ag yields, especially through the subtropics, which are the part of the world where currently the majority of the grain crops are grown, where the climate models are consistently projecting decreases in available precipitation and temperatures that become challenging, at least for the currently available crops. It's very difficult to say that we ought to be building in a big increase or a big decrease. I think that to be responsible in the thinking now, we ought to recognize that there's a range of possibilities as a consequence of increased investments in ag yields. When you talk about where things have happened across the R&D space, there's been a very depressing fall off in investments in primary agriculture as a target for improving technology, and with any of the outcomes we're talking about, increased ag investments are going to be one of the most compelling arguments.
The FAO projects that we have 1.4 billion hectares that could be non-forested land that would be good or very good to grow crops and don't today, and that we need 70 million. That's 5% of that to feed the world in 2050. That doesn't make them right. It's just one estimate.
So let me just briefly respond to Stephen and to Nate. First, Stephen, I think you're absolutely right that while the models sort of paint a broad brush picture of unmanaged ecosystems, and those those classifications are embedded in the models like ours. The realization that the details do matter, and you actually do need to go to finer spatial and temporal resolutions, has actually been the defining characteristic of the research frontier in these models. How do we couple up to models that actually give us that information? The models are actually not about what's the right thing to do. They're about, what's the consequences, more to Jessica's point, what's the consequence if we go down this path versus that path, and as opposed to what's the right path. Actually, Nate, you make a really good point, and when this unintended land use change emissions first came out, we wrote a paper back in 2008, which was actually, we had exactly the same question you did. How much of this is due to the fact that we have an externality that we're pricing in one part of the global system and not in the other? And we just ran these two side-by-side cases in this paper where Marshall Wise was the lead author on, and we published it in Science, and it couldn't be more stark. I mean, what you see is if you don't value the carbon on the landscape, you do get this unintended consequences. You get massive land change emissions. Once you start valuing the carbon, there's, as Chris was saying, there's about 500 petagrams of carbon above ground, another maybe 1,200 petagrams of carbon in the below ground carbon system. If you put pretty much any value on that much of anything, you begin to treat it fundamentally differently. And what happens is that the model says, this land is very valuable. The unmanaged ecosystems extraordinarily valuable. In fact, the model wants more of it because it says, this is something that you're valuing. It actually afforests as well as producing bioenergy, and it produces the bioenergy with the CCS to minimize the bio footprint. And that's actually one of the things that is really important, that the CCS actually reduces the bio footprint because it allows you to meet any emissions. If you're going zero, you get to zero more easily if, in fact, you don't return the carbon that was taken out of the atmosphere back to the atmosphere. If you put it into some long-lived repository, it actually minimizes the bio footprint. Great question.
Great, thanks. Yeah, I mean, kind of building off of this, but also thinking beyond the model results and the embedded assumptions. And again, in this context of decarbonizing the last 20%, do you have a sense, and you've started to answer this, I guess, but do you have a sense of the greatest needs in terms of either offsetting or replacing fossil-based fuels in transportation? Is it offsetting through BECCS emissions that are either coming from transportation or industry or some other parts of our energy system? And do you also then comparing that with the kind of reasonable assumptions you might make where there's a range of them about the scale of the resource? Do you see the ability of bioenergy to be able to fulfill all of those kinds of needs in this context of the last 20%, or might we be hitting up against those kinds of limits of how much resource there actually is to meet those needs in the last 20%?
So that was just a comment. Yeah, I just wanted to make a connection, I think, between what we were talking about today and maybe yesterday. I was, just curious and looking up that we talked about cement and we talked about steel. Well, the third industry sort of slice of the pie that has, in terms of direct emissions, is petrochemical industry and chemistry industry. So, especially I think in the context of limited land resources and stuff, we have to think about what the, and especially in the context of the last 20%, we have to think about what the draw on bioresources for bioproducts to be able to feed a bioplastics industry and feed a chemical industry and all this kind of stuff would be. So
Today,
perhaps that's just a comment, yeah.
79% on a mass basis of the output of the U.S. refining industry is fuels of one kind or another. 4% is chemical feedstock. So fuels is the big one.
That was
For petroleum refining, but that's what we get plastics and petrochemicals from.
We're down to 3 minutes. And should we wait a long time?
Okay. So far the discussion here is very US-centric. When I think about China, I noticed there's a very important pathway we almost never mention here, like methanol. Because right now they are using coal to make methanol and fuel and all kinds of chemical now. It's very dirty. But one argument for that is in the future, because you already have the infrastructure, you can replace coal with biomass. And because the capital is already there, so the capital cost is already gone, and then that would be an easier way to transition into biomass. But I suspect there are still a lot of gap in technology by replacing coal with biomass, and maybe the supply issue. But I think that's probably a very important thing to look into. Thank you.
You know, Chigen makes a really important point that throughout this meeting, one of the things we keep coming back to is the idea that flexible supply pathways and flexible processing strategies are extremely important. And one of the interesting features of the current thermochemical refining industry is that it does have the potential to let us use alternative feedstocks for alternative products. And when we think about food, biomass trade-offs, one of the things that potentially important is emphasizing plant types, crops, that have the potential to be directed toward alternative uses, food-related uses, fuel-related uses, storage-related uses, and that constraining opportunities may represent a risk that looks very unattractive in the long run, even if emphasis on, for example, a biomass-specific crop like miscanthus might provide slightly higher yields.
Ines gets the last one.
Thank you. So we've been asked about, in the surveys, about R&D allocation and so on. So what I would like in terms of comment from the panel is, in terms of R&D efforts globally in other regions too, and developments, both for biofuels and bioenergy, who are the leaders and what are the prospects and examples of things that have actually worked nicely so far? More in a global perspective, it seems that the discussion tended to be just a little bit US-centric. Looking at the IEA projections for bioenergy, for example, the US is flat and the growth is in Europe and in China. So could you comment a little bit more on that?
You can start.
Give that to Lynd.
Yeah, the biggest R&D efforts in bioenergy that I know of correlate reasonably well with the size of current bioenergy utilization, So the US has historically had a big effort and has one ongoing. Brazil has a major effort as part of, mostly out of the Sao Paulo Research Foundation. Europe has somewhat smaller efforts. There are other places, India's is smaller, South Africa's is smaller, Argentina's is smaller. So there are efforts around the world. I think most of them, I don't know how many of you are familiar with the book Pasteur's Quadrant, but I think most of the research that's done is either in Bohr's quadrant or Edison's quadrant, and the place that could make the most difference is actually in Pasteur's quadrant, where you're not afraid to learn something new or try something new, but you actually are trying to get something done, as opposed to, we have a sort of a bimodal distribution of R&D with a valley in the middle, and I see a lot of countries, especially that are relatively new to the game, who run the risk of being the last people to look at the old paradigms. So I don't think it's a very forward-looking R&D field in general.
We're at break time, but I see Jack came back and the sign is long. Can we sacrifice 2 minutes? Give Jack?
I think we were
Oh, well, sorry.
And maybe I could just say one. I thought we were all going to say something in response to Inez's question, and it is really important what the R&D portfolio should look like. And I think right now the real weakness is in the R&D portfolio on ag sustainability, and I think that globally we need to see a real revitalization of ag research as a key enterprise.
Yeah, just pick up on, just make one quick little comment. You get that dichotomy between the basic science and the application in spades in the U.S. Department of Energy, where you've got the bioenergy research program, and then over in the Office of Science, you have this basic science and genomic science. And trying to get those two married up is really a difficult task.
A big picture question for Jay. I really liked your description of the IAMs discovering BECCS. And it seems like, one interpretation of that is that they discovered BECCS as a specific technology, and as a big picture point, the other interpretation could be that they just discovered that it's really helpful to have a backstop mitigation technology when we're trying to figure out how to get to ambitious temperature targets. So in this theme of considering the last 20% in a context where we will have mitigation risks, for example, BECCS might not scale, what do you feel like are the most important features of what we learned from the IAMs about the backstop or about trajectories through time in a situation where BECCS may or may not scale as they assume?
You want to take the last two, and then I'll just, I'll take my part of it.
Okay. Mine's totally a different topic. So why don't you please address that?
Okay. All right, so let me just respond quickly. And that is, I think that the whole point of these integrated assessment models is to give you these insights that you didn't know when you started the experiments. And that's probably the most important thing you learn from these models, is that, the systems actually have their own consequences, that it's not simply adding the individual components together. And that's probably the most important thing that you get out of these models.
Last question. Okay, so the first is a comment, and I want to speak in favor of what Dan started talking about, what Klaus addressed, and what Lee is suggesting, and that is that we aren't intending for the bioenergy crops to meet 100% or even a big fraction of what we demand in our energy system. I think there is a strategic need and a good opportunity for us to focus that small amount of energy contribution into, for example, heavy-duty transportation, aviation, things like that. And secondly, I think there are some no-regrets technologies that we can invest in immediately for using, for example, waste biomass on already used croplands, no additional, although some may argue that we should take those lands back for prairie lands and things like that, but no additional impact on land use or anything else. This is what I think we have to focus on in the bioenergy area. But lastly, I want to interject one final comment that is perhaps a risk, which is the air quality topic. That is one we haven't talked a lot about, although I heard you mention it, Lee. Because some of the conversion strategies on the back end could impact air quality. So to me, that seems like the only risk for some of this small amount of the last 20% we want to get out of bioenergy.
I need to say one quick
Okay, that'd be great.
As a part-time regulator, our resources board, dealing with this from a policy perspective, these issues about the use of land, agriculture, from a policy perspective, Jessica started this discussion, are so hugely important, but it's going to be so hugely difficult to deal with. Energy is much easier. Regulating land, regulating agriculture, it's diffuse, it's hard to deal with, and all of these sustainability concerns are really valid, and we've got to understand they're probably not going to be handled well by the policy process.
Just really quickly response to Jack's. I think that Jack reiterated what all of us have been saying. There is a biomass opportunity, and it is going to be concentrated on topics where there's the potential for win-wins, and it's not going to be gigantic compared to the scale of the global energy system. If those are the three takeaways from this morning's discussion, I think we've made fabulous progress.
Good to end with a positive note.